And I want to thank the organizers for inviting me to the seminar. It's always a pleasure to to talk about polynomials, orthogonal polynomials. All right, and so I want to talk today about a work that uh, I'm doing, and it's a joint work with Teresa Perez, which is most commonly known as Maite from Universidad de Granada. She's one of my advisors, my thesis advisors. And now we are both advisors of Marlon Recarte, okay, who is doing his PhD in Granada as well, but he is from Universidad Nacional Autónoma de Honduras. Okay, so we are both from the same place, and we are doing our work under the supervision of. Well, I used to do my work with Maite as my advisor, but now we are both uh, are working with Marlon to direct his dissertation. Okay, so this is before going into what we're trying to do. I just want to give a quick summary so that we can have a bit of a bird view of what we're trying to do. Okay, so in this work, we are trying to study the orthogonal expansions or Fourier series with respect to an orthogonal polynomial basis associated with this inner product that I have here, which is an inner product that is defined on the unit ball of RD. Okay, and it also has a term that lives on the surface or the sphere of this ball. Okay, and why are we choosing this inner product? Well, uh, Yuan Shu studied this part right here, the big part, the one that's defined on the ball, uh, as as part of a study of spectral methods or numerical methods for a nonlinear boundary problem defined on the ball. And the basis, the orthogonal basis with respect to this inner product, is an adequate basis to approximate the solutions of this boundary problem. And the idea of this work is to extend this inner product into something that includes the boundary of the domain. In this case, it's the sphere. So that's why we are adding this term right here so that we can control the values of the function on the boundary. Okay. And of course, this is a Sobolev inner product because it includes differential operators. As you can see here, we have the Laplacian, okay, acting on both of the functions, and that's why this is a Sobolev inner product. The steps that we're going to take in this work are very simple. So we are first going to construct an orthogonal basis for this inner product. And once we have this construction, we are going to look for properties that we can later use in order to in order to study the approximation properties of the Fourier series. One thing, I cannot see the chat, so if there's a reason for me to stop, just let me know. Okay. All right. The I have organized the work as follows. So first, I'm going to start with some preliminaries, and I'm just going to remind very few things about orthogonal polynomials in one variable, and then I'm going to go a little bit more slowly uh, to talk about orthogonal polynomials in several variables. Okay. And then I'm going to talk about the classical orthogonal polynomials on the ball. Okay. And I'm going to center my attention on the construction because I'm going to use this construction or the idea of the construction for the classical polynomials to construct a basis for the Sobolev orthogonal polynomials. Okay, and once I have this construction, I'm going to find some properties as well, and then I'm going to talk about the Fourier series with respect to this inner product. Okay, and if I have time, At the end, I'm going to talk about another inner product, a related inner product that consists in replacing the spherical term with the evaluation of the functions on the origin. Okay, so it's just like putting a Dirac delta on the origin. And something curious about this part, the last part, is that we were not expecting to have results on about this inner product. Okay, so these came as a surprise after we have understood the very first part, and then we went into studying other kinds of inner products, and we ended up with some nice results about this other inner product. Okay, so I'm going to start just reminding a little bit because I'm assuming that everybody here is very familiar with orthogonal polynomials. So I'm just going to go a little bit fast, and I'm going to try to tell you the difference between the univariate case and the multivariate case. So first of all, I'm going to denote with pi the linear space of univariate polynomials. And here I'm going to have a bilinear form defined on polynomials. And in this work, I'm going to consider those polynomial sequences such that the nth element of the sequence is a polynomial of degree n. Okay, so so this is the basis of the polynomials, and I'm going to say that whenever I'm going to call an orthogonal polynomial sequence uh, if whenever you evaluate the bilinear form with two different elements of the basis, then the result is zero, the value is zero, and if I evaluate the bilinear form with the same element, then I have a value that is different from zero. And of course, if these are all positive, I have a norm squared. Okay. All right. So whenever I have the unitary case, I can apply a Gram-Schmidt procedure to the sequence of monomials in the natural order. Okay, so whenever you apply orthogonalization to this sequence, what you will obtain is an orthogonal polynomial that is orthogonal to all polynomials of degree less than n. Okay, you will obtain one polynomial of orthogonal polynomial of degree n, and also this is a unique polynomial up to multiplication factor. And I'm saying this because this does not occur in several variables. Okay, so I'm going to mention it in a few slides, but I just want you to keep in mind that there's a difference between one variable and several variables. Okay, so one example, and I'm going to mention the example that I'm going to use, or the family of orthogonal polynomials that I'm going to use throughout this work, and it's the Jacobi polynomials. And everybody knows that is a family of polynomials that depends on two parameters, alpha and beta. The nth orthogonal polynomial in this family is expressed in this form. Okay, and they are orthogonal with respect to this bilinear form, which consists in an integral from -1 to 1, okay, with respect to a weight function, which is defined down here. And as you can see, it also depends on the two parameters. And of course, by making an change of variables, you can translate the orthogonality from the interval -1 to 1 to any other bounded interval. Okay. Some of the properties, as you already know, there are several properties of classical Jacobi polynomials, and I'm just here mentioning some of the properties that we use throughout this work. Okay, that the derivatives of Jacobi polynomials are again Jacobi polynomials with a shift in the parameters. They satisfy a second order linear differential equation with polynomial coefficients. Okay, and these are the eigenvalues of the associated with each polynomial of degree n. Okay, and then there are other recurrence relations which basically link one family with parameters alpha and beta with families with different parameters. Okay, so here in red you can see the families that have different parameters. Okay, and I'm going through these very fast because I'm assuming that everybody are familiar with this one, but these are some of the properties that have been used throughout the work. Okay, so here I'm going to go a little bit more slowly, okay, because this is um, the slide about orthogonal polynomials in several variables. So in this, um, um, D is going to be the number of variables that I will be using, okay, and pi super D it just denotes the linear space of real polynomials in D variables. Okay, so something that does not happen in one variable is that in several variables, uh, there are many linearly independent polynomials of degree n. Okay, in one variable there's only one, but in several variables there are many. And in particular, this is the amount of linearly independent polynomials of degree n that you have in D variables. Okay, just as an example, we can take the number of variables equal to 2. And here I have listed the monomials into variables. I have ordered them in a certain way, okay? But there is no natural order for the monomials in more than one variables, okay? So there's one difference with the univariate case, okay? And here, for instance, there's one monomial of degree 0. There are two monomials of degree 1, three monomials of degree 2. And in general, there are n plus 1 monomials of degree n, okay? And like I said, there's no natural order of for the monomials. So whenever you apply the Gram-Schmidt process, okay, you will get many orthogonal bases. Okay, there are as many bases, orthogonal bases, in several variables as there are ways to order the monomials. Okay, even so, if you order them according to the total degree of the monomials, among the elements of the same degree, there's also no natural order in which you can put the monomials. Okay, so uh, if you order them according to the total degree, what you're going to get is an orthogonal basis that is where each element is orthogonal to every polynomial of less degree. Okay, but you don't know anything about what happens between elements of the same degree. Okay. Uh, I'm going to consider our sequences of polynomials, okay, where here I'm denoting by p super n those polynomials of total degree n, and I'm considering sequences of polynomials where there are as many linearly independent polynomials of the same degree as monomials of degree n. Okay, so uh, that condition tells me that this sequence has to be a basis of polynomials of degree of d variables. Okay, so these are the sequences that I'm going to consider. So once I introduce a bilinear form, I can define the orthogonal polynomial systems. Okay, which is basically whenever I evaluate the bilinear form uh, with a polynomial of total degree d and another polynomial of less degree, the value of the bilinear form is 0. So if all the polynomials satisfy this orthogonality condition, I say that this is an orthogonal polynomial system. Okay, and I have said nothing about what happens when I put another polynomial of the same degree over here. Okay, so this is a nuance of the multivariate case. Okay, but if I have a basis such that uh, distinct elements of the sequence are also orthogonal, then I say that this is a mutually orthogonal polynomial system. Okay, so it doesn't matter if they are of the same degree, but if they are distinct elements, then this is a mutually orthogonal polynomial system. Okay, so here, these quantities that are denoted by the h with the subindices, whenever these are a non-zero values, but whenever they are positive, of course, they are squared norms of the elements of the orthogonal system. Okay, but from now on, I'm just going to say that they are norms, even though they are norms squared. Just for short, I'm just going to call them norms. Uh, so in order to establish some notation, I'm just going to mention some of the differential operators and other families of polynomials that are going to appear in this work. So first of all, delta just denotes the usual Laplace operator, which has this expression in Cartesian coordinates. But also, I'm going to use spherical polar coordinates, which are uh, a representation of points in RD with a parameter that is non-negative, which is basically the norm of the x, and uh, this letter, which I can remember the word, it's just an element of the sphere. Okay, I think this is called chi. I can't remember, but basically these are the spherical polar coordinates, and in these coordinates, the Laplacian operator has this representation where it has a radial part, and it also has a spherical part, which is this notation over here, and it's called the Laplace Beltrami operator. Okay, which is a differential operator that acts on the spherical parts of the variable. Okay, and this is just the restriction of the Laplace operator to the sphere. Uh, we are going to use harmonic polynomials in the variables, which are homogeneous polynomials that satisfy the Laplace equation, which means that they are um, uh, they belong to the kernel of the Laplacian. Okay, and I'm going to denote by this symbol the space of harmonic polynomials of degree n. Okay, and this space has a dimension given by this number that I have over here, but I'm just going to summarize this number with this symbol right here. Whenever we restrict the harmonic polynomials to the sphere, that means that when r in the spherical coordinate representation, when r is taken to be exactly equal to 1, we have the spherical harmonics. Okay, and one property of the spherical harmonics is that they are eigenfunctions of the Laplace Beltrami operator, just like I have shown here. Okay, and another important property about the spherical harmonics is that they are orthogonal with respect to this inner product defined on the sphere. And as you can see, this is one of the terms that appear in the inner product that I want to study. So it is natural for me to be mentioning the spherical harmonics at this point. Okay. Uh, all right. So that was just a small reminder and setting notation for the rest of the work. And now I'm going to talk about the classical orthogonal polynomials on the ball. Okay, so these are very well studied polynomials. There's a lot of literature about these polynomials. One particular reference is the book by Dunkel and Shu. Okay, and there are several bases that are orthogonal on the ball, but I'm going to use one particular basis that's going to be useful for me in the rest of the work. Okay, and this basis is composed by polynomials, okay, that are constructed in this form, okay, where the first part is a Jacobi polynomial, okay, where you can see that the first parameter is fixed, okay, is a parameter that is strictly greater than -1, and the second parameter is not fixed. It depends on the total degree of the polynomial and on the degree of the Jacobi polynomial that appears over here. Okay. Also, this part over here makes this Jacobi polynomial orthogonal on the interval 0, 1. Okay. And it also makes this a radial function. It only depends on the norm of the x. So this is radial. Okay, and then there's a second factor, which is an element of an orthonormal basis of the harmonic polynomials. Okay, so I will consider, or we can consider this part as the spherical part of the polynomial, right? So this polynomial has total degree n, all right, and these are form a mutually orthogonal basis of the linear space of orthogonal polynomials on the ball with respect to this uh, bilinear form or inner product that I have over here. And as you can see, here we have a weight function that is defined on the ball. It's of this form right here. It is also a radial function, and the parameter appears as an exponent over here. Okay, and then these are the norms, and they are all positive. That's why I'm calling them norms. Okay, and they have this expression over here. Okay, so I want you to remember, and I want to emphasize that this has one radial part composed of the Jacobi polynomials and one spherical part composed of the harmonic polynomials. And whenever j is equal to 0, or in other words, when the Jacobi polynomial has degree 0, then this classical orthogonal polynomial coincides with a harmonic polynomials. This is going to be important later on. One property that is satisfied by the classical orthogonal polynomials on the ball is that they also satisfy a second orthogonality relation. Okay, and in this case, I can say that the gradients of the Jacobi polynomials satisfy this orthogonal relation with respect to this weight function, where the parameter is this is the same weight function as before, but the parameter is not mu. It is instead mu plus 1. Okay, and here the norms are related to the classical norms because they are just multiples of the classical norms. And here the multiplication factor is given by this expression. Okay, so we can study the orthogonal expansions with respect to the classical basis, uh, and I can define the orthogonal expansion for any f, okay, that is L2, that is in L2 of this. Basically, it's a weighted L2 on the ball. I can decompose it into uh, this representation over here, where the Fourier coefficients are given in the standard way. It's just the inner product of f with the corresponding element of the basis, okay, divided by the norm of the corresponding element of the basis, right? And one thing that we can notice here is that uh, if I take these two summations, uh, what they are doing is basically projecting the function into the space of orthogonal polynomials of a certain degree. Okay, therefore I can define a projection operator by taking this part of the series, okay, and call it a projection operator. So this takes any function in L2 and projects it into the space of orthogonal polynomials of degree m. Okay, and then using these projections, I can define the partial sum operator, okay, by adding all of these projections up to degree n, okay, and this is just the partial sum of the Fourier series of f. Okay, so the first one projects functions into the space of orthogonal polynomials of degree m, and the second operator projects any function onto the space of polynomials of degree at most n. All right, and we can also define the error of approximation by polynomials with respect to the classical inner product, okay, which is defined as the infimum taken over all polynomials of degree at most n of this error right here. And it is well known that if I replace this polynomial by the partial sum operator, okay, of degree n, then this infimum is achieved, okay? And we have the following result by Piñar and Xu, okay? The states that this error has a convergence rate given by this power over here, okay, 2s. And there are two other error terms involved, okay, and that the rate is associated or is related to the order of the differential operator that appears here, which is something that appears in the classical analysis of Fourier expansions. Okay, but in this case, I need two elements. Okay, because whenever the function is spherical, whenever I take when f is spherical function, then this term does not contribute to the error to this bound. Okay, and if the function is a radial function, then this term does not contribute at all, and we only have this one contributing to the bound. Okay, and when the function is neither radial or spherical, then um, both errors um, contribute to this bound. Okay. All right, so that's some of the results about classical polynomials on the ball and some of the approximation properties. And now I'm going to go ahead and talk about our results, okay? Which is, first of all, just to remind you that our motivation comes from the study by Yuan Shu, okay, where he constructed an orthogonal basis for this inner product, and this orthogonal basis is used to efficiently implement spectral methods for the nonlinear Poisson equation that I have shown over here, okay, with zero boundary conditions. So our idea was to extend Schu's result by including this term over the sphere, okay, which is the boundary of the domain that appears over here, the ball, okay, so that we can control the values of the function on the boundary, okay. So this is the motivation of our work, and just to fix some notation, I'm going to denote by H super S the Sobolev space of continuous functions where the derivatives up to order S uh, are in L2. Okay, so these are the functions that we are going to approximate, and just to remind you that this is the induced norm with respect to the inner product. Okay. All right. So our first result consists on the construction of an orthogonal basis with respect to our inner product. Okay, and here is our result. Just like in the classical case, whenever j equals 0, this basis coincides with the harmonic polynomials. And when j is different than 0, uh, the construction is very similar as the classical one, where we have a radial part and we have a spherical part. Except that in this case, there are some differences. And one of the differences is that we have a term that vanishes on the sphere. So this term actually kills the spherical term in the inner product. Okay. Another difference is that the fixed parameter, okay, has to be equal to 2. And this is because this is the necessary value for this parameter so that we can have the orthogonality, okay? But we also have a Jacobi polynomial, okay? This is a polynomial of total degree n, okay? And we can actually compute the norms. Here we have the norm when j equals 0, and here we have the norm when j is different than 0. And as you can see, this is just a multiple of a univariate Jacobi norm, okay, with one parameter equals 0 and uh, the other parameter, the same one that appears over here. Okay, so the way to prove this result is just by taking uh, the Sobolev bilinear form evaluated in two different elements of this basis, and then making a change of variable to spherical polar coordinates. And when you do that, what's going to happen is that the inner product is going to split into two parts. one part is the orthogonality for the Jacobi polynomials, and the other part is just going to be the orthogonality for the spherical harmonics, or for the harmonic polynomials. No, for the spherical harmonics. Okay, so what you're going to get is a multiple of two norms. Okay, so whenever the two elements are distinct, one of the two norms is going to be equal to zero. That's why this is a mutually orthogonal basis. All right. So once we have constructed the basis, we look for some properties that might be useful for us later on in order to study the approximation properties. Okay. And one of the properties that we found is that the Sobolev basis is related to the classical one with parameter equal to zero. Okay, in this way over here. Here, this is a differential operator, the same one that appears on the inner product. Okay, so whenever you apply this differential operator to one of the q's, what you obtain is a multiple of a classical polynomial on the ball. Okay, and these quantities that appear over here are different than zero. And the way to prove this is just by changing to spherical polar coordinates, and using the properties that I have mentioned at the beginning, the properties of the Jacobi polynomials that I have mentioned at the beginning. And then it's just a matter of simplifying whatever you get, and little by little, you will obtain the expression for the classical uh, polynomials on the ball. Okay. It happens that whenever you commute this factor with the Laplacian, okay, and you apply it to the classical basis, you will recover the Sobolev basis in this form. Okay, but in this case, not all of the coefficients that appear are going to be different than zero. Here, some of them are going to be equal to zero. So it is natural to make the composition of these two differential operators, and what you obtain is um, a differential equation of order four, satisfied by the Sobolev basis. Okay, where these eigenvalues are given right here. Okay, so we have found um, a differential operator or differential equation satisfied by the Sobolev basis. And it is clear that if you already have this relation for the q's, you can actually use it to prove the orthogonality. Okay, and when we were working at the beginning with this basis, we did all of the computations to prove the orthogonality, okay, just like I mentioned before. And then we discovered this one. And of course, when we wrote the paper, we wrote it in the other order, so it could be a little bit more elegant, okay? But the natural way that we did this was we first proved the orthogonality, then we discovered this one, okay? By just changing to spherical polar coordinates. Okay. Another property that we found is that there's another relation between the Sobolev basis and the classical basis, except that in this case, the parameter, the fixed parameter, is 1. Okay. So when j equals 0, when this parameter over here is equal to 0, then the Sobolev and the classical basis coincide. Okay. But whenever j is different than 0, the Q is just a linear combination of two classical ones, okay? One classical polynomial of total degree n, and another classical polynomial of degree n minus 2, okay? Here, there's a gap. Here, the polynomial of degree n minus 1 is missing, okay? And this is because of the symmetry of the ball and the fact that the inner product preserves the symmetry of the ball. Okay, it is well known that whenever you have the symmetry of the ball and an inner product that preserves the symmetry of the ball, all of the terms that appear in an orthogonal basis will have total degree of the same uh, of the same parity as the n over here. So if n is even, all of the monomials that appear over here are also uh, of even degree. Okay, if n is odd, then all of the monomials that appear over here are going to be of degree odd. Okay, so in order to for that to be true, for that to be satisfied by this side of the equation, you also have to have the same property on the right hand side. So that's why we are skipping uh, the polynomial of degree n minus 1. All right, so once we have constructed the basis and acquired some understanding about the basis, we go ahead and try to study the approximation properties of this basis. So first, we define the Fourier coefficients in the standard way, just like this. I'm going to, instead of having here a parameter like in the classical case, here I have a delta uh, to denote that this is the Fourier coefficient with respect to the Sobolev basis. Okay, and then I can define the projection and the partial sum operators in the same way as in the classical basis. Okay, so our first result says that these Fourier coefficients, the Sobolev ones, okay, even though the inner product involves differential operators, you can represent the Fourier coefficients without involving the derivatives of f or of the basis. So in this case, this Fourier coefficient can be computed by these two integrals, one on the ball and one on the sphere, but none of them involves the derivatives of either f or of the basis. Okay, and when j is equal to 0, okay, then the Fourier coefficients, if you look closely, they coincide with the Fourier coefficients with respect to the spherical harmonics. So what this is saying is that this basis, this Sobolev basis, reproduces the values of the function whenever you restrict it to the sphere. Okay, just because I'm going to use a lot this operator, I'm going to give it a special name. It's just a calligraphic D. Okay, and just to remind you that this calligraphic D associates the Sobolev basis with the classical one, and that these quantities over here are all different than 0. So there's a one-to-one correspondence between the two bases of polynomials, which makes this a bijection, this calligraphic D, a bijection on the polynomials. Okay, so one of the results that we can deduce from that fact is that since the projection, this projection operator is basically an orthogonal polynomial with respect to the Sobolev inner product, whenever you apply the calligraphic D, this calligraphic D just converts this projection into an orthogonal polynomial of the same degree, but with respect to the classical weight with parameter equal to 0. Okay, and then in turn from this result, we can deduce something that I usually call a commutation property, which is not really a commutation property, but it's easier to say it that way because whenever you interchange the partial sum operator with a calligraphic D, what happens is that the partial operator becomes a classical partial sum operator with parameter equal to 0, and the D can be pushed inside of the partial sum operator like this. Okay, so it's a kind of commutation operation, but it's not really. It's just easier to say it that way. Okay, once we have this commutation operator, I can deduce some relationship between the classical and the Sobolev Fourier coefficients. Okay, and they are related in this form. And these are important because later on, I can use this property to deduce the relationship between the errors of the classical basis or the classical approximation and the Sobolev approximation. All right. So one of the first results that we got is about the errors. Okay, so let me define the Sobolev error just in the similar way as in the classical one. Okay, and because of the bijection that exists or that is given by this calligraphic D, then the error with respect to the Sobolev basis behaves like the error of the classical basis whenever we try to approximate d of f. Okay, this is that's the intuitive explanation, but of course, in order to prove this, you have to do all of the computations. So the proof consists on just expressing this as a sum and then replacing the Fourier coefficients, the Sobolev coefficients, with the classical coefficients, replacing the Sobolev norms with the classical norms, and just doing the asymptotic analysis. And what you get is that they behave similarly, or they behave the same way. Okay. All right. So the big theorem of our work is this one. Okay, which is some kind of simultaneous approximation uh, given by the partial sum, the Sobolev partial sum, for these three errors that I have over here. Okay, so these three errors involves differential operators of degree 0, degree 1, and degree 2. Okay, and then they can be bounded by a classical error. Okay, so I'm just going to give a glimpse of the proof. Okay, I'm going to do it really fast. Okay, uh, but something that you have to take into account is that we did not prove it in this order over here. Okay, what we did was first prove this one, the first one, because it's very easy. Then we proved the last one, okay, which involves much more effort. And once we got these two, we proved the one in the middle. Okay, because in order to prove the one in the middle, we had to use these two. All right, so the first one, okay, we start from the left-hand side, and then I use the commutation property of the calligraphic D and the partial sum, and now this becomes just a classical error, and that's it. That's just equal to the classical error. That's the proof of the first one. Okay. Okay, so remember that now I'm going to try to prove this one. I already have this one. I want to prove the last one. Okay, so I start from the left hand side. Okay, and I use some duality argument, which is supposed to be well known. I didn't know about this, but it's called the Aubin-Nietzsche technique. And what it does is, uh, since L2 is its own dual, we can think of this element of L2 as a linear functional, okay? And the norm of that linear functional is by definition, or it can be characterized by this supremum over here. So my task will be to bound this supremum on the right hand side, okay? In order to do that, I will introduce the following auxiliary boundary value problem, okay? Which has a unique solution for every G in L2. This has a unique solution, okay? And this boundary value problem, okay, comes from the fact that uh, I want to bound the previous supremum, okay? So whenever I apply Green's identity several times, to apply Green's identity to the left-hand side over here, which is the Sobolev inner product, okay, where this function that appears over here comes from this part, okay, from the solution for some certain for certain G. This is the solution of the problem, and since it vanishes on the sphere, I can write it in this form. So whenever I try to compute this inner product and I use Green's identity several times, I will have some elements that are defined on the boundary, okay, and another part that is defined on the ball, okay. So I collect everything that is defined on the sphere I collect them in the boundary conditions, and the part that is defined on the ball, I collect it over here. So since I'm using the solution of this boundary problem, uh, then this Sobolev inner product becomes this classical inner product, where now I have the G and I have this error multiplied by this factor over here. Okay. Another thing that I use is the well-known fact that this error, f minus its nth partial sum, is orthogonal to every polynomial of degree at most n. In particular, it is orthogonal to the partial sum of degree n of this red function that I have over here. Okay, so I can put it inside without changing anything, and using this fact, I can bound this right hand side, okay, by this quantity over here where I have introduced the nth partial sum of phi tilde, okay, and then I use Cauchy-Schwarz inequality to split this into two parts, okay. Here I have an error that does not involve G, and here I have another error that involves G, okay. So if I put this on the previous supremum, okay, I can take out everything that does not depend on G out, and now I have this new supremum that I have to bound. All right. So I'm not going to go into details. I'm just going to say that after applying several results, like for example, the relationship between the Fourier coefficients of the Sobolev basis and the classical basis, the relationship between the norms, etc., I can bound this error, okay, by this quantity over here, okay, which my goal was to make uh, this over here appear, which is basically what I wanted, because I'm taking G as the solution, as the right hand side of our boundary problem, and phi sub G is the solution of that boundary problem. So this is, I can replace this by by G, by the norm of G. Okay, and over here I have finally found the power of n that I was looking for, and just by dividing both sides by the norm of G, okay, I have a bound for this supremum over here. So this supremum is bound by some constant divided by n squared. Okay, and I can finally write the left hand side, okay, bounded by this quantity over here. And we already know that this quantity over here behaves just like a classical error of df. Okay, so I have proved the first part, I have proved the third part, and I want to use, prove the middle part. Okay, so in order to prove the middle part, I use an equality called the Landau-Kolmogorov inequality. Okay, and it just says that I can bound the uh, the partial derivative of some function, okay, by the norm of the function, the square root of the function, uh, and the square root of the function, the Laplacian of the function, okay? But the Laplacian of this function is just the calligraphic d of uh, f and s, okay? So I already have these two bounds. I put them together, and I have the bound for the partial derivative that I wanted to prove, okay? So that was the big theorem, okay? And I will mention really quickly our other results, where we can replace what we did was replace the spherical part with the evaluation of the functions at the origin. Okay, so here we have a new bilinear form. Okay, and of course we started by finding an orthogonal basis with respect to this bilinear form, and we used the same idea as before. And here is our construction. Okay, just as before, when j is equal to 0, then the orthogonal basis coincides with the harmonic polynomials, just like in the previous two cases, okay, the classical and the Sobolev. And when j is equal to 0, different than 0, I'm sorry, we have a radial part and a spherical part. And one difference is that instead of having something that vanishes on the sphere, I have something that vanishes on the origin. Okay, which makes sense. It kills this part. And now instead of having the first parameter fixed, in this case, it's the second parameter that's being fixed. And then the first one depends on the total degree and on the degree of the Jacobi polynomial. And something else that happens is that instead of having an orthogonality on the interval 0, 1, okay, we have something similar, but instead of integrating from 0 to 1, we are integrating from 1 to 0. Okay, so before, the orthogonality, or the way that we integrated on the ball, was from the center to the sphere. And in this case, what we're doing is evaluating this integral from the sphere to the origin. Okay, once we have the construction, we started to look for similar properties as before. And something that happens is that we also have a relationship between this new basis uh, with the classical one with the same coefficients. So in this, we are starting to feel a little bit suspicious. Okay, and we kept on finding similar properties, and we got the same relationship with the classical basis, but in this case, it's there's a factor of -1. Okay, so that means that this new basis R is just a multiple of the basis Q. Okay, where j equals 0, the coefficient is 1, and when j is different than 0, the coefficient is -1. All right, so this new basis is the same one as before. Okay, so that means that the previous basis that we have constructed is also orthogonal with respect to this new inner product. Okay, we started looking more closely to the Fourier coefficients. Okay, and when n is bigger than 0, then the Fourier coefficients coincide. But the very first coefficient, the one corresponding to the degree 0 of the polynomial of degree 0, then the Fourier coefficient is a little bit different, where you can see that the element on the origin has its contribution. Okay, and but uh, overall, we just can say that the basis that we have constructed previously is an orthogonal basis with respect to an inner product that involves a term that is constant, a mass term on the origin, and also has a spherical contribution. Okay, and then the other part remains the same. And just to finish, I'm just going to mention a few references. Most of the approximation theory results that we have used can be found in this book. Okay. Uh, uh, then this other book that I had mentioned before is a very good book that collects the theory of several variables, in particular orthogonal polynomials on the ball. The classical basis that I have shown appears on this book. Um, the big part of our inner product, the one that has already been studied before by Shu, appears on this article. Okay, and then that trick that I used in order to prove the approximation property. Okay, that dual argument is found in this article by Shu, and then the results for the approximation properties of the classical basis can be found on this article. So I think that that's it, and thank you for your attention.